So let's finish things off here with a trick for actually computing limits. For instance, let's say for some reason you were studying the function sine of pi times x divided by x squared minus 1. Maybe this was modeling some kind of dampened oscillation. When you plot a bunch of points to graph this, it looks pretty continuous. But there's a problematic value at x equals 1. When you plug that in, sine of pi is, well, 0. And the denominator also comes out to 0. So the function is actually not defined at that input, and the graph should really have a hole there. This also happens, by the way, at x equals -1, but let's just focus our attention on a single one of these holes for now. The graph certainly does seem to approach a distinct value at that point, wouldn't you say? So you might ask, how exactly do you find what output this approaches as x approaches 1? Since you can't just plug in 1. Well, one way to approximate it would be to plug in a number that's just really close to 1, like 1.00001. Doing that, you'd find that this should be a number around -1.57. But is there a way to know precisely what it is? Some systematic process to take an expression like this one, that looks like 0 divided by 0 at some input, and ask what is its limit as x approaches that input. After limits so helpfully let us write the definition for derivatives, derivatives can actually come back here and return the favor to help us evaluate limits. Let me show you what I mean. Here's what the graph of sine of pi times x looks like. And here's what the graph of x squared minus 1 looks like. That's kind of a lot to have up on the screen, but just focus on what's happening around x equals 1. The point here is that sine of pi times x and x squared minus 1 are both 0 at that point. They both cross the x-axis. In the same spirit as plugging in a specific value near 1, like 1.00001, let's zoom in on that point and consider what happens just a tiny nudge dx away from it. The value sine of pi times x is bumped down, and the value of that nudge, which was caused by the nudge dx to the input, is what we might call d sine of pi x. And from our knowledge of derivatives, using the chain rule, that should be around cosine of pi times x times pi times dx. Since the starting value was x equals 1, we plug in x equals 1 to that expression. In other words, the amount that this sine of pi times x graph changes is roughly proportional to dx, with a proportionality constant equal to cosine of pi times pi. And cosine of pi, if we think back to our trig knowledge, is exactly -1. So we can write this whole thing as -pi times dx. Similarly, the value of the x squared minus 1 graph changes by some dx squared minus 1. And taking the derivative, the size of that nudge should be 2x times dx. Again, we were starting at x equals 1, so we plug in x equals 1 to that expression, meaning the size of that output nudge is about 2 times 1 times dx. What this means is that for values of x which are just a tiny nudge dx away from 1, the ratio, sine of pi x divided by x squared minus 1, is approximately -pi times dx divided by 2 times dx. The dx's here cancel out, so what's left is -pi over 2. And importantly, those approximations get more and more accurate for smaller and smaller choices of dx, right? So this ratio, -pi over 2, actually tells us the precise limiting value as x approaches 1. And remember, what that means is that the limiting height on our original graph is evidently exactly -pi over 2. Now, what happened there is a little subtle, so I want to go through it again, but this time a little more generally. Instead of these two specific functions, which are both equal to 0 at x equals 1, think of any two functions, f of x and g of x, which are both 0 at some common value, x equals a. The only constraint is that these have to be functions where you're able to take a derivative of them at x equals a, which means that they each basically look like a line when you zoom in close enough to that value. Now, even though you can't compute f divided by g at this treble point, since both of them equal 0, you can ask about this ratio for values of x really close to a, the limit as x approaches a. And it's helpful to think of those nearby inputs as just a tiny nudge, dx, away from a. The value of f at that nudged point is approximately its derivative, df over dx, evaluated at a times dx. Likewise, the value of g at that nudged point is approximately the derivative of g, evaluated at a, times dx. So near that trouble point, the ratio between the outputs of f and g is actually about the same as the derivative of f at a times dx divided by the derivative of g at a times dx. Those dx's cancel out, so the ratio of f and g near a is about the same as the ratio between their derivatives. Because each of those approximations gets more and more accurate for smaller and smaller nudges, this ratio of derivatives gives the precise value for the limit. This is a really handy trick for computing a lot of limits. Whenever you come across some expression that seems to equal 0 divided by 0 when you plug in some particular input, just try taking the derivative of the top and bottom expressions and plugging in that same treble input. This clever trick is called L'Hopital's rule. Interestingly, it was actually discovered by Johann Bernoulli, but L'Hopital was this wealthy dude who essentially paid Bernoulli for the rights to some of his mathematical discoveries. Academia is weird back then, but hey, in a very literal way, it pays to understand these tiny nudges.